Welcome to another inorganic chemistry lesson. Today we'll be talking about university level oxidation reduction. This method is very advantageous because usually we get almost all the coefficients we need to balance the reaction. To use this method, you must either have acidic or basic conditions. Let's start the reaction between permanganate and iron 2 ions in acidic solution. When we are using the redox method, we don't look at the element's oxidation state, but are looking at the whole ion. In our first half reaction, permanganate ion becomes manganese 2 plus ion, and in the second one, iron 2 plus became 3 plus cation. Let's deal with the first half reaction. We have the same amount of manganese in both sides, but a different number of oxygen atoms, 4 and 0. To balance oxygens, you always add the same amount of water molecules on the different side. In this case, we add 4 H2O molecules to the right side. Now we have equal amount of oxygen atoms, but notice that we also got hydrogen atoms present. To balance those, we add H plus ions to the other side, so 8 in total. All particles are now even on both sides, and only now we can calculate the total number of electrons in the half reaction. To do that, we simply look at the oxidation state of each ion. Before the reaction, we have 1 minus and 8 pluses, so basically the overall charge is plus 7. After the reaction, water is neutral, so it doesn't have a charge, and manganese is 2 plus. We can equalize the charges by adding 5 electrons to the left side. And now both sides have an equal charge. The second half reaction is a lot simpler, because we don't have oxygen atoms present in it, so we don't need to add water molecules. To balance the charges, we add 1 electron to the right side of the equation. Permanganate ion was reduced, and iron 2 plus ion was oxidized in the chemical reaction. Because we have a different number of electrons in our half reactions, we must even them out. We multiply the first half reaction by 1 and the second one by 5. We get 5 Fe 2 plus, reaction arrow, 5 Fe 3 plus 5 electrons. Now finally, what we need to do is sum up both half reactions to one big reaction. We add all compounds before the reaction and then add all compounds after the reaction. What we get is MnO4 minus plus 8H plus 5 Fe2 plus, reaction arrow, Mn2 plus 4H2O plus 5 Fe3 plus. Note that electrons cancel out to give us the final balance equation. And that is our introduction to redox reactions under acidic conditions. Now let me remind you of the general rules you must follow when balancing reactions with this method. We must always have 2 half reactions. If we need, we balance the center element first. We add water only when we need to balance oxygen. And after that, we always add H plus ions. We balance charge using electrons, and if necessary, we multiply one or both half reactions. Lastly, we add both half reactions and cancel identical species. If you follow these rules, you should do fine with this method. Now let's look at another reaction between dichromate ion and sulfur 4 oxide. The first rule was to write half reactions. Dichromate ion became chromium 3 plus ion, and sulfur 4 oxide became sulfate anion. Let's start with the first half reaction. We need to balance the center element which is chromium. So we write 2 in front of Cr3+. Now to balance oxygen, we add 7 water molecules to the right side. And to balance hydrogens, we add 14H plus to the left side. The last thing to do is to balance the charge using electrons. Dichromate charge is 2 minus, and we have 14 hydrogen with plus charge, so the overall charge before the reaction is plus 12. After the reaction, water is neutral and 2 chromium 3 plus gives us 6 plus charge. To even out charges, we add 6 electrons to the left side. On to the second half reaction. The central element is balanced, so we can start with oxygen. We have 2 on the left side and 4 on the right, and because of that, we add 2 H2O molecules to the left side. On the other side, we add 4 H plus ions to balance the hydrogen atoms. Now to balance the charge, we add 2 electrons to the right side, because before the reaction we have only neutral compounds, and after the reaction we have 2 minuses and 4 pluses. Because we have a different number of electrons in our half reactions, we must even them out. We multiply the first reaction by 1 and the second one by 3. After we multiply the reactions, we have an equal number of electrons in both half reactions, so we can add them up. Once again, we add all compounds before the reaction, and then we add all compounds after the reaction. What we get is Cr2O7 2 minus plus 14H plus 3SO2 plus 6H2O reaction arrow 2Cr3 plus 7H2O plus 3SO4 2 minus plus 12H plus. The last thing we need to do is to cancel identical species. We had 14H plus before and 12 after the reaction. So we subtract one from another and are left with only 2H plus before the reaction. The same goes for water, but in its case, we are left with one H2O molecule after the reaction. Now let's write a fully completed reaction. Cr2O7 2 minus plus 2H plus 3SO2 reaction arrow 2Cr3 plus H2O plus 3SO4 2 minus. For the last two examples, I want to show you this method with actual reactions. The first one is a reaction between copper and diluted nitric acid. Let's write ion charges for this reaction. Pure copper is 0, hydrogen plus, NO3 is minus. In copper to nitrate, copper is 2 plus, and nitrate, once again, is minus. Because NO and H2O are neutral compounds, we don't write charges for their elements. We only write charges for compounds that can be divided into ions or are pure elements. Now let's look which particles changed their oxidation state. Pure copper became copper cation, and nitrate ion in nitric acid became nitrogen 2 oxide. We don't need to add water in the first half reaction because there is no oxygen present, so all that's left is to balance the charge with electrons, plus 2 electrons on the right side. Now in the second reaction, we add 2 water molecules to the right side to balance oxygen and 4 H plus ions to the left side to balance hydrogens. To balance the charge, we also add 3 electrons to the left side, and both half reactions are completed. Now to even out electrons, we multiply the first reaction by 3 and the second one by 2. As you can see, there is no difference between the reaction made from ions, like in the first two examples, or the actual reaction which we have here. The order in which we solve the redox reactions are always the same. Okay, now all that's left is to sum up both reactions. In this case, we get 3Cu plus 2NO3 minus plus 8H plus, reaction arrow, 3Cu 2 plus 2NO2 plus 4H2O. Now basically, what we got is the coefficients in the actual reaction. We can write 3 in front of the pure copper. How about the coefficient in front of HNO3? Because we can choose between 2 and 8. The answer is always the number of H plus ions you have in the completed half reaction, because H plus stands for acid in the reaction, and we ignore the side ion. Going forward, we have 3Cu 2 plus ions in the half reaction, so we can write 3 in front of CuNO3 times 2, 2 in front of NO2, and 4 in front of H2O. As you can see, we got all the coefficients we needed from the half reactions. Therefore, this method is very advantageous, as I mentioned before. The last example, under acidic conditions, I prepare for you is a potassium bromide reaction with potassium permanganate and sulfuric acid. Once again, we look at charges. Potassium plus, bromide minus, potassium once again plus, permanganate minus, hydrogen plus, sulfate 2 minus, pure bromine 0, manganese 2 plus, sulfate 2 minus, potassium plus, sulfate 2 minus, and water is a neutral compound. Which ions change their oxidation state? First is a bromide ion, which became pure bromine, and the second one is permanganate ion, which became manganese 2 plus cation. Our first half reaction should look like this. Bromide lost an electron and became pure bromine. For the second half reaction, we have MnO4 minus plus 8H plus 5 electrons, reaction arrow, Mn2 plus 4H2O. We multiply half reactions by 5 and 1 and add both of them together. So what we get is 5Br minus plus MnO4 minus plus 8H plus, reaction arrow, 5Br plus Mn2 plus 4H2O. All that's left is to write coefficients in the reaction. Now the important thing to note is pure bromine. In a half reaction, we have 5 bromine atoms, but in a chemical reaction, we already have 2. Because we don't write a fraction as a coefficient, we multiply all coefficients by 2 in the chemical reaction. So we have 5Br2, and in front of Br minus, we write 10 and not 5. The same goes for MnO4 minus and Mn2 plus. Instead of 1, we use the coefficient 2. In front of sulfuric acid should be 8, because we already have 2 H plus ions in the compound. And lastly, in front of the water, we write 8 as well. All that's left is to balance potassium atoms in K2SO4. Before the reaction, we have 12 potassium particles, 10 from KBr and 2 from KMnO4. So after the reaction, we write 6, and the reaction is balanced correctly. Now it should be clear how to use redox under acidic conditions. Then how about basic conditions? Let's look at the first example, where permanganate ion reacts with oxalate ion. A very important thing to note here is permanganate ion transformation. Under acidic conditions, MnO4- always transforms into Mn2 plus ion, but under basic conditions, we always get manganese 4 oxide. Let's quickly write half reactions for this example. What we do now is the same as we did under acidic conditions. We balance the center element, then add water to balance oxygen, and add hydrogen ions to balance hydrogen atoms. In the first half reaction, we add two H2O molecules to the right side and four H plus ions to the left side. In the second half reaction, to balance carbon, which is center atom, we write 2 in front of CO2. Notice that now we have an equal number of oxygen atoms in both sides, so we don't need to add water molecules. All that's left here is to add 2 electrons to the right side to balance the charge. Let's get back to the first half reaction. If we have a reaction under basic conditions, we add same amount of OH minus ions on both sides as we have H plus ions in the half reaction. In this example, we have 4 H plus ions, so I add 4 OH minus to the left and to the right sides. Now on the left side, we have the same amount of H plus and OH minus ions, which we can convert into water molecules. So we eliminate both of those ions and instead we write 4H2O. Now we can cancel water molecules. So in the end, we are left with MnO4- plus 2H2O, reaction arrow, MnO2 plus 4OH-. Last thing to do here is balance the charge. On the left side, charge is -1, and on the right side, charge is -4. So we add 3 electrons to the left side. Now we multiply the first half reaction by 2 and the second one by 3. And after that, we add both of them together. As you can see, redox under basic conditions is practically the same as under acidic conditions. The only difference is to add OH minus ions to the half reaction. So our final half reaction should look like this. 2MnO4- plus 4H2O plus 3C2O4 reaction arrow, 2MnO2 plus 8OH- plus 6CO2. Let's do one more example, but this time we'll be using full reaction. Potassium cyanide reacts with potassium permanganate and water to produce potassium fulminate, manganese 4 oxide, and potassium hydroxide. Let's assign oxidation states. Potassium is plus, cyanide minus, potassium plus, permanganate minus, water neutral, potassium plus, fulminate minus, manganese 4 oxide neutral, potassium plus, and OH minus. We can see that Cn minus became CnO minus, and MnO4 minus became MnO2. In the first half reaction, we add one water molecule to the left side and two H plus ions to the right side. Now to convert acidic conditions to basic conditions, we need to add two OH minus ions to both half reaction sides. 2H plus and 2OH minus can be replaced with two water molecules. And now we can cancel water molecules on both sides. So we are left with one H2O molecule on the right side. Lastly, we add electrons to the right side to balance the charge. Let's do the same thing to the second half reaction. We add two H2O molecules and four H plus ions to the different sides. Then we add four OH minus ions to both sides. On the left side, four H2O molecules are created, which can cancel two HO2 molecules on the right side. Also, we add free electrons to the left side to balance the charge, and half reaction is completed. Now we multiply the first half reaction by 3 and the second one by 2. We get 3Cn minus plus 6OH, reaction arrow, 3CNO minus plus 3H2O plus 6 electrons. And the second reaction, 6 electrons plus 4H2O plus 2MnO4 minus, reaction arrow, 2MnO2 plus 8OH minus. We can sum up both reactions and we get 3Cn minus plus 6OH minus plus 4H2O plus 2MnO4 minus, reaction arrow, 3CNO minus plus 3H2O plus 2MnO2 plus 8OH minus. We can cancel OH minus ions and are left with 2 on the right side. And also we eliminate water molecules and are left with one H2O molecule on the left side. All that's left is to write coefficients in the actual reaction. 3 in front of KCN and KCNO. Also, we can write 2 in front of KMnO4, MnO2, and KOH. And in front of water molecule, we don't write anything. Now, we have a fully balanced reaction under basic conditions. Thank you for watching this lesson, and please subscribe to this channel for more chemistry content. And like always, I leave a few exercises with answers that you can try on your own, and see you in the next lesson.